questions that I haven't really looked at beforehand, so I'm supposed to do them kind of like at first glance. And yeah, so first of all, if anyone is interested, I know no one is watching right now, I think, but I think this might be saved on YouTube afterwards. So, you know, if you're watching this video from the beginning, or if you watch this video from the halfway point, and if you want to know where I'm doing the problems from, the book is Frank White, and the name of the book is Fluid Mechanics. So it's Fluid Mechanics, and I think it's the 4th edition. So that's those are all the details so far. So yeah, this is where I'm going to take the problems from. I think this is a really good book. It's got a variety of questions. I've actually done some of the questions from the book previously on the channel, and yeah, last week I was teaching hydrostatics in uni, so I thought to myself, why do I not make a live stream where I post some hydrostatics questions? And give me 1 second, I'm just trying to see if I can it shows this is live, but I might have to do some tweaking. Okay, it says it's live. Yes, okay, I think it should work. In any case, right, OBS is still behaving. I've got 1 spectator. Yeah, it's my first time doing this kind of thing, so there's oh hi, Yadav Hari Haran. Yes, it is live. See, I said your name, so it's definitely not pre-recorded. Yes, it is. It's 100% live, so you'll be able to, you know, rewatch it afterwards if you want, but there isn't really anything much to rewatch at this point because I just started. And what I was saying is that I'm gonna go through a couple of questions from this textbook, and all the questions are gonna be strictly on hydrostatics, and those are questions that I haven't really seen beforehand. I mean, I know they exist, I glanced over them, but I haven't really like solved them beforehand. So yeah, I'm going it sort of blind. So in any case, right, let me start then. Let's see if everything is working as it should. Just doing another double check on OBS. Hello, Suyal, I'm not sure how to pronounce it, sorry if I'm butchering your name. Hello from the UK. Glad to have you around. So let's see here. Okay, so the first question that I'm gonna look at is this one. So just a basic hydrostatics question. I just want to get my calculator ready. Yeah, I'm just curious, are you guys students? Are you in university? Are you pre-university? Are you teaching? Are you lecturers? I'm curious what my audience is, where my audience is from. So let me know in the comments, and then I'll check it in a bit. Anyway, so let's have a look at this question. Now, you might have noticed that I put this table beforehand because some of the questions will require knowing some properties of certain fluids. More specifically, we're just looking at hydrostatics, so there's no viscosity or anything like that that we care about. So the only thing of note here is the density of each fluid. So we have everything from hydrogen to air, gasoline, water, and so on. The ones that we're going to use the most are probably water, and I've also seen this one. It's a type of oil. Then there is glycerin, and of course mercury is quite common as well. Oh, okay, I see. student of civil engineering, student in Coventry for aerospace, but will reach only on the 4th. Okay, I see. So you're not yet in Coventry. You're gonna arrive a bit later. Yeah, understandable. Well, I'm looking forward to seeing you in class soon. Okay, so let's move on to this question. So, nice hydrostatics question. We have a tank, and in this tank there is air, there's gasoline, and then there's glycerin. I think that's how you pronounce it. And we know a couple of things. So we know that pressure gauge A reads 1.5 kilopascals. So essentially what that means is that the pressure of the air here is 1.5 kilopascals. Gauge. So the word gauge, we're going to come back to this in a second, but let's read the question as well. So the fluids are at 20 degrees Celsius, okay? And then determine the elevations Z in meters of the liquid levels in the open piezometer tubes B and C. Okay, so essentially this is a static problem, right? It's hydrostatics. It's from the chapter of the book called Hydrostatics. And what we have to find is the elevation. So this is the thing that we need to know, right? The elevation of the liquid levels in the open tube. So we have two open tubes. We have tube B and C because A is not open, right? A is closed and there's a pressure gauge which reads something. So we've got, let's use some good colors here. So we've got this, which is, let's call it Z2, or let's just call it Z1. Why not? We'll call that Z1 and this one Z2. And yeah, I think that's pretty much it in terms of unknowns. Right, so the way in which I would do this is I would use that what I call the horizontal line test to figure things out. So what I like to do is I draw a dotted horizontal line which passes through the same liquid. So let's, for example, let's consider that boundary between air and gasoline, right? So we've got, use a thinner line for this. So we have this boundary right here, which crosses, so if I continue this, it's gonna cross through tube B at that point, and it's gonna cross through tube C at that point as well. Sujal, am I saying this right? You can let me know. Which faculty teacher are you? So I'm teaching aerospace engineering. Yeah, that's my main job, and this is one of the modules that I teach, fluid mechanics. So yeah, I just decided to, you know, expand on what I normally give my students in terms of tutorial questions. So this is something that would be slightly, it's within the syllabus in a way, but it's a bit more, it's extra pretty much, just to put it this way. So yeah. Now, in terms of finding Z1 and Z2, what I would first do is I would say, okay, let's try to find Z1, right? And with this horizontal line test that I was talking about earlier, what I would suggest is once you draw the horizontal line, what you then have is that the pressure at every point along that horizontal line is equal as long as that line crosses through the same fluid. So in other words, the pressure here is the same as the pressure here. The pressure here is equal to the pressure here, but it's not equal to the pressure outside, because outside there is, you know, atmosphere basically, and yeah, it won't work. But in this case, we can say that the pressure at this point, let's use a different color for this, So the pressure at this point is equal to the pressure at this point, right? And this is what we can use to figure out the pressures, and we can use that to figure out the elevation values, Z1 and Z2. So we're going to start with Z1, and I'm going to call this point A. No, not A. We have ABC already. I'm going to call this point 1, and this point, or I'm going to call this point 1 because I already did, and this one is going to be 3 because I'm going to reserve 2 for Z2. Okay. So what we can say first of all is that P1 is equal to P3, right? So the fluids are kind of all connected to each other, and at 3 and at 1 we have the same liquid, we have gasoline, right? So 3 is the boundary between air and gasoline, and 1 is gasoline. So because I have the same fluid in both cases, I can safely say that P1 is equal to P3, right? If they're not equal to each other, then it would the liquid would start moving around, which it's not happening because this is a hydrostatics problem. Have a good night, Sujal. Definitely have to go to bed if you have lectures tomorrow. Right. Okay. Good to know that we have an international audience. So let's try to write things down in terms of those heights. So the pressure at 1, this is based on the atmospheric pressure. So we're going to look at what liquids are there on top of point 1, right? So we have the atmosphere, which is PA plus, and then we have this this tiny bit of fluid which is gasoline, and we know that that small column of gasoline is also creating pressure, basically. So we have the density of the gasoline times, or let's use capital G, times G, which is the gravitational acceleration, and then times the height. So the height in this case would be Z1 and then minus 2.5, right? So Z1 minus 2.5, because Z1 is the unknown elevation and 2.5 is basically this, right? So the difference, that tiny bit of gasoline, is above that dotted line by this amount, okay? And then the pressure at 3 equals, so the pressure at 3 is equal to the pressure at this point here, which is what the gauge is reading. It's the 1.5 kilopascal. So I'm going to call that P capital A, not to be confused with P lowercase a. This is, maybe I should write down. So PA, this is atmospheric pressure. So if I'm using lowercase, it's atmospheric. If it's capital, it's the pressure at point A, right? Now the pressure at A is given in gauge. So I'm working in absolute pressures here. So if I want the absolute pressure at A, I just take this 1.5 and I add the atmospheric. And you know what, actually, let me just call it ATM. I think that's probably better. Yeah, ATM, atmospheric pressure, right? And then plus, we also have then this column of air. So this column of air is also pushing down on point 3. So that is going to be given by rho gauge, right? Which is the density of air times G, and then times 2 meters. So I'm just going to put times 2. And that's basically it. So we have everything, right? We have all the data that we need, and then this is just one equation with one unknown. Hello, Professor Greg, I'm MSc. Oh, good to see that that we have MSc students interested in this. This is really great. Good to see that there's a variety of university students, aerospace, civil engineering, space engineering. So the more the merrier. Sir, if at ATM is positive, both sides wanted to cancel each other out. Yes, that it will. That's a very good point. That's exactly what I was going for. So what I'll do is I'm gonna cancel this and this, and now I just have to work to find what Z1 is, right? So let's try to rearrange. So we have the density of the gasoline, G, Z1 minus 2.5 is equal to the pressure at A plus rho air G times 2. Yeah, well spotted, Yadav. If I make any errors in calculations, you're going to be held accountable. Yeah, you have to pay attention to what I'm doing. Okay, so if we rearrange this, then I can extract Z1 minus 2.5 by writing it as PA plus density of air times G times 2 over density of gasoline times G. Okay, cool. So at some point I'm gonna start adding in numbers, but I want to delay that as much as possible because I don't really like using numbers from the beginning, although I have a couple of things plugged in already. So Z1 is 2.5 plus PA plus density of air, so I'm just copying what I have above, divided by this. Okay, so then we have 2.5 plus, and now we can put the numbers in. So the pressure at A is 1.5 kilopascals, which I'm not gonna leave it like that, I'm gonna convert it. So it's gonna be 1500 plus, now the density of air, we go to this table, and we're gonna use 1.2 for the density. So it's gonna be 1.2. For the gravitational acceleration, we use 9.81 times 2. So in some cases, the question would tell us if we are allowed to use 10 or 9.81, right? Typically, in some cases, you're told that yes, you can use 10 because it just makes the calculations better, but it's not necessarily more realistic. So we're just gonna stick to 9.81. And then this is divided by the density of the gasoline, which is 680, right? So I'm looking at this. So this is 680, and this is multiplied by, again, 9.81. So now we just plug the numbers in, and we'll see what we get. Right, so on the top I have 1.2 times 9.81 times 2 plus 1500, so this is 1523.54, and this is 680 times 9.81. You can tell I haven't actually done this before, so it's the first time going through the calculations myself. So 1523.54 divided by 6670.8 plus 2.5. Okay, so I get a value of 2.72, or if you round it up, 73 meters. Okay, so what this means is that this distance Z1, so the height of the fluid in that B tube is 2.728. Yes, I think it's 2.728 when you plug it in, but if we use two significant decimals, then it would just be 2.73. Yeah, good job, Yadav. That's actually the more accurate answer, but I'll stick it to 2.73 meters like this. Okay, cool. So hopefully that's all clear. Now, what I'll do now is I'll repeat the process, but for the tube C, for the glycerin or glycerin. I never understood how this is supposed to be pronounced. Okay, so just copying the diagram again. 1 second. Okay, there we go. So, you still recording? Yes. Okay. Right. So Z, how do they call this? Z2. So this is Z2. And then we do the horizontal line test again. So this time I'm gonna draw another horizontal line, but I'm gonna draw it. Let's use a thin line, and let's actually do it this way. I'm gonna do this. Okay, this looks a bit better. So now what this means is that the pressure everywhere along this line, as long as it passes through the same fluid, will be constant. So I'm gonna say that the pressure here is equal to the pressure here. So I'm going to call this point 2, and I'm going to call this point, I called it 3, let's call it 4. So I can say that P4 is equal to P2. So this is the equation that I'm going to start from, basically, right? So we've got the pressure at 4, which we can express as rho gh and a couple of things. So let's go through this again. So the pressure at 4 is due to the pressure at A. So basically what's happening is that every layer is pushing down onto point 4, right? So we've got, first of all, we have the pressure at A. So I'm gonna break it down like this. So the pressure P4 is equal to P capital A plus the atmospheric pressure, right? Because PA is gauge, so we add atmosphere and we get absolute. Plus, then we have to take into account this much of the column of air, basically. So that's going to be density of air G times 2. So this term, we also used it in this other part of the previous analysis when we looked at tube B, but it also appears here because it was pushing down at point 3, so it's clearly pushing down on 4 as well. So yeah, we have this, and then the extra thing that we now need to use is the fact that P4 also takes into account this much height. Okay, so this is going to be equal to, what does P capital A stand for again? So P capital A is this. So P capital A is 1.5 kilopascals. So this is the reading of this gauge. So this, let's put it here as well. So the gauge reads 1.5 kilopascals, and it reads the pressure where the gauge is mounted, basically, which is here. So it's the pressure at this point, at the very top of the closed container. So yeah, hopefully that makes sense. So we've got the height of the gasoline to take into account. So that's going to be density of the gasoline times G, and then times 1.5. And that's it. That's the entirety of P4, right? And then we look at P2. So P2 is based on just two things. So we have atmospheric pressure, so PATM. Okay, plus we have now this tiny amount of glycerin height, right? Which is density of the glycerin. I have to find a new way of calling it. I'm going to call it GL for glycerin or glycerin. And then G, and then that height difference, right? This here is given by Z2, which is unknown. Let's use consistent colors. Is given by Z2 minus 1, like this. Yeah, so Z2 minus 1 is exactly what I'm looking for, is exactly this amount that is balancing the pressures. So now all we have to do is we equate them because they're equal according to what we were discussing earlier. So we've got one is equal to the other, so I'll just write the whole thing again. So PA plus PATM plus rho air G times 2 plus density of the glycerin G 1.5 is equal to atmospheric pressure plus the density of the oh sorry, this is gasoline, not glycerin. This is GL is glycerin. G and then Z2 minus 1. Okay. Yes, we're all good. Okay, so as before, we cancel out the atmospheric pressure. And now we rearrange to get Z2. So what I'll do is I'll put this on the next page. And I'm gonna rearrange. So I want this by itself, which it already is by itself. So density of the glycerin G Z2 minus 1 equals, and then we have the pressure at A plus air density G times 2 plus density of the gasoline G times 1.5. Yeah, I kept saying density of the glycerin, but it was gasoline, and thankfully I actually used the correct density when I did the calculations previously. So that's all good. Okay, so Z2 minus 1 is equal to, so all this stuff gets divided by density of the glycerin times G. So now I just get rid of this minus 1 and I add it here like that. So Z2 equals, and now once again we put the numbers in. So this is the number crunching part, where this is 1500. Density of air, I think this was 1.2. Yeah. This is 1.2, this is 9.81, this is 2. The gasoline, just to double check, was 680. And then we have 9.81, 1.5. Right, and then this is divided by the density of the glycerin, which is, now we use it for the first time, it's 1264. So 1264 times 9.81 and then plus 1. Okay, so now we just have to plug the numbers in, so I'll do the top first. I like to do them bit by bit. So 1.2 times 0.81 times 2 plus 680 times 9.81 is 1.5, 1500. Okay, so the top is 11,529.74 and the bottom is 1264 times 9.81, which is 12,400 roughly. I'm just gonna write it like this, plus 1. Okay, so finally we get an answer which is it's close to 2 meters but not quite, so it's 1.92 meters. Yeah, 0.929, and then you add that to 1 and you get a value of Z2 which is 1.929, or yeah, so I think it's roughly, I'm gonna write it here, that this is roughly 1.93 meters. Alright, good that we have someone who's following along. Good job, Yadav. So yeah, that's basically how this works. So you just do that horizontal line test twice and you're done. And yeah, that's basically it. Okay, cool. Right, let's have a look at something else. So I think we can just have a look at the next question, really. So 2.12, this looks relatively interesting. Right, so let's have a read through it. Do we have to learn by? No, you do not have to learn by heart all the densities. I don't know by heart all the densities. I was just using this table here. If, I mean, you know, this works, this is applicable to any student from any university. If you are in a fluid mechanics exam and you're given any kind of more exotic fluids other than water, you don't have to remember it. They should be given to you, right? So the only one that I would remember is that of water, which is, I mean, here it shows as 998, but no one actually uses that in calculations. We all use density of water as 1,000 kilograms per meter cubed. And maybe you can also remember the density of air, but even that is, from my experience, it's given to you in exams. So yeah, realistically speaking, this is the only one you need to know. Everything else is, you know, should be provided. So yeah, but what I do recommend knowing is some features about some liquids. For example, you know that the density of oil is less than the density of water. No one is asking you to tell you to say the value of the density of oil, because it depends on the oil, right? So this is just one type of oil, but if you look at, I don't know, extra virgin olive oil, that's probably going to have a different density. Also, mercury is quite prevalent, and this is a density that I do remember. I know it off the top of my head. I would say it's about 13,500 or 600 kilograms per meter cubed. Yeah, again, you don't have to remember it. It should normally be given to you, but what you should know at least about mercury is that it's much heavier than water. Alright, so the density of water is 1,000, that of the mercury is 13, almost 14 times higher. So, and that's basically it. Okay, so in this question we have another container. Yeah, there's only questions with containers for the most part, because it's hydrostatics. There isn't really anything too interesting happening, to put it this way. So we know that the tank contains water and immiscible oil. So immiscible, as far as I know, means that it's not mixing with the water. Okay, and then what is the height h in centimeters if the density of oil, so see, this is one example when we are given the density of oil, because we don't even know what kind of oil we're dealing with. So we know the density of oil is 898 kg per meter cubed. We know the density of water. See, so this one is not given, but that's why we should at least try to remember it as 1,000. Like this. And that's essentially it. And then we know a couple of heights. So we have to find h such that this configuration is possible, right? So let's have a look at what's happening. So we have a tube which has, we have a tank with two tubes going up, and on the left side there is some oil, and on the right side there's mostly water. Yeah, oil, there's only oil for a bit, and then there's this wall which is separating the oil from the rest of the body of water. Yeah, and we know certain heights. We know that this is 8 centimeters. We know that the layer of oil in the tank itself is 12 centimeters, and then we have an unknown height from the tank into the tube. And then we know that on the right hand side, the water goes up from the tank into the tube by an amount of 6 centimeters, and then we don't know what this is. So how do we figure that out? Well, what I would do here, as before, I would just apply the same principle, which is just draw your horizontal line and and that's basically it. So I'm gonna draw my horizontal line here, like this, and I'm gonna call this point 1, and I'm gonna call this point 2. And because we have the same fluid on both sides, so again, at 1 we have oil and water, and at 2 we have just water. You know, we can basically say that it's the same, you know, we have the same fluid appearing on both sides. That means that P1 is equal to P2. So what does that mean? Well, we can actually express them in a more explicit way. So we have P1. So P1 is based on, yes, exactly. So P1 is equal to P2, and P1 is based on the fluid above point 1, right? So we probably have atmospheric pressure. I mean, we definitely have atmospheric pressure, but like before, you'll notice that atmospheric pressure isn't actually doing anything. So it will cancel out. And then we have plus. So above point 1, we have some height, right? So we have the total column that's pushing down on point 1 is this. And I don't really care about the fact that I have different widths, because the only thing that matters in hydrostatics is how much height you've got above a certain point, right? So that's why when you dive in the sea, for example, or in a lake, the only thing that matters is that how deep you are, because based on that, the pressure on your eardrums is going to increase. It doesn't matter how much you swim sideways, it only matters how much you swim up or down. Yeah. So we've got atmospheric pressure, and then we have the hydrostatic pressure of the oil. So we have the density of oil times G, and then we have the height, which is H plus 0.12, right? Because I'm using meters, and you should use meters rather than centimeters as much as possible. So that's P1. And then P2, we've got a similar case. So we've got atmospheric pressure plus density of water times G, and then times, so we know how much this is, right? So we know this is going to be just 18 centimeters. So we've got 0.18. So we equate the two pressures. So we have P1 is equal to P2. Therefore, we have density of oil G, and then we have this is equal to this. I've already cancelled the atmospheric pressures, so I don't have to write them again. And then we cancel out the G's, which is nice because now we have a different, well, we have a more succinct expression. So P1 is density of oil G. Yes, yeah, that's pretty much it. So when you rearrange, remember we're trying to find H here. So we have H plus 0.12 is equal to 0.18 raw water divided by raw oil. Okay, so I'm gonna say that H is 0.18 density water over density oil minus 0.12, and then if we plug the numbers in, this should be 0.18, this is going to be 1000, this is going to be 898, and this is going to be 0.12, and then finally, let's see, so 0.18 times 1000, yeah, so this is basically 0.08 meters. Yes, correct. 0.08, or if you want to convert back into centimeters, this is 8 centimeters. Yeah, so that's the end of the question, pretty much. 8 centimeters, yeah, not 8 meters. That's a big difference. Yeah, so again, pretty straightforward. There isn't really anything uh, different. I mean, it's a bit more straightforward than the previous question. There weren't as many calculations to do. Now, I'm looking at this and trying to think which one to go for. Okay, let's try maybe the next one. So I'm looking here at okay, so the text of the problem is this one, and it's got a diagram as well. And the diagram is this right here. So this is not too different. I guess the only difference is that it's got 3 liquids instead of 2. And we still have to find the height. So yeah, let's try to read the question first, and then we'll see how we can approach this. Big mistake, 8 centimeters, 8 meters. It's okay. I mean, as long as you're not doing the same mistake when you're designing something that people's lives depend on, it's okay if it's just doing it in a question. As long as you identify it and sort it out. Right, so should we draw 2 lines here? That's a good question. So should we draw 2 lines? We could draw 2 lines. Let's think about it. So if I decide to draw a line above, so if I make the first line here, right? Because it kind of looks like we could draw 2 lines, right? So we can draw a line here and a line here, basically. So let's think about it. So this line passes through both sides, and there's, you might then think, okay, I'm gonna say the pressure here is gonna be equal to the pressure here, but that's not actually correct. The pressure here and the pressure here are actually not equal to each other. And the reason for that is because the line doesn't actually cross through the same liquid. So at point 1 we have water, we have just water, and at point 2 we have gasoline, which is having an interface with this other liquid. I don't know what it is, I'll just call it liquid. So therefore the pressures at 1 and 2 cannot be equal to each other. Yeah, exactly, because we have 2 different fluids. Now if we draw the line below, which is here, then yes, we can say that, and this is actually how I think this problem wants to be solved. The other thing I wanted to mention is that this question tells us something about this thing called SG, which is given to us as 1.6. So SG, I mean, if you're watching this, you might know what it stands for, but this is an abbreviation for specific gravity, which is a fancy way of saying that the liquid, whatever this is, the ratio between the density of the liquid and the density of water is 1.6. Yeah, so that's basically it. So the density of the unknown liquid is going to be 1600 kilograms per meter cubed as a result of that. So I'm gonna remove this because this is not correct, and I'm going to draw my line here, but with a different color. like this. Okay, so if I call this point 1 and this point 2, now it should work, right? So the pressure at 1 is gonna be equal to the pressure at 2, because now I have water and liquid, right? So I'm gonna get rid of this because it's gonna be in the recording anyway. And then at 2 I'm gonna have just the unknown liquid. So we have a match, so the pressures are the same. So now we just continue with our usual way of solving this, right? So the pressure at 1 is equal to, well, we just have water on top, and I'm completely gonna ignore atmosphere right now, so I'm just gonna use the gauge pressure or the hydrostatic pressure. So that's density of water G times 1.5, which is 1,000 times, actually I don't know why I'm doing this, I'm gonna leave it as it is, and then I'm gonna rearrange. And then the pressure at 2, this is going to be based on the column of gasoline and the small column of the liquid. So now I have to take into account two things. This is, or let's say this is one of them, and then this is the other one. So yeah, this is what we have to write. Now, how would this work now? So the pressure at 2 is based on the density of gasoline, so we used capital G for this, times G, and then we have this height here to express in terms of, you know, certain things. So this should be, we know the total depth of the tank is 2.5 meters. Yeah, so we have 1.5, I think that's 1.5. I hope I didn't cut it in the wrong way. Yeah, that's 1.5. This is 1.5, this is 1, so the total is 2.5, which means this height should be 2.5 minus h. Yeah, because I have the unknown value h there, so yeah, the you know, the gasoline takes the remaining part. So this is going to be 2.5 minus h. Okay, plus, so now we have the liquid, so we have density of the liquid times G, and then this is multiplied by that remaining bit. Waste P2 is equal to the density of point 2 is, yeah, it's not touching the gasoline, but the gasoline is still pressing down on it, essentially. Yeah. So this height here should be this tiny bit that I drew here, an arrow for. This should be h minus 1. Yeah, so that's what it is. So, and then we have the height of the mysterious liquid is h minus 1. Okay, and I think we're pretty much done. So now we can rearrange and we can find what h should be. So if I make P1 is equal to P2, I have density of water G, and then I have 1.5, it's equal to density of the gasoline G, and then I have 2.5 minus H, plus the density of the liquid G, and then H minus 1. Okay, so I can cancel out the G's, which means it doesn't matter which planet we're on. So now we just have to move things around and rearrange and make H the subject. So let's see how I can actually do this in an easier way. I think I should probably leave H on the right. So I have raw water times 1.5, and then minus the density of the gasoline times 2.5, and then this should be plus density of the liquid times 1. So yeah, so I'm bringing all the known things to the left, and I'm keeping the h's on the right. So on the right I should be left with h, and then I have rho L minus rho G. Yeah, I think this works. So I have positive numbers on both sides. I don't like getting negative numbers on the sides if I can. It's just just to tidy things up. So the H therefore is density of the water times 1.5 minus density of the gasoline times 2.5 plus density of the liquid over rho L minus rho G. Okay, so we know everything is just, one equation, one unknown. So let's see, let me write this a bit better. So this should be 1.5. Don't know why there's this extra dot here. So density of the water times 1.5, this is 1500. Density of the gasoline, I think this is not given in the question, but that's why I had this table here. So that's 680. 680, 2.5 plus, this is 2.5. Density of the unknown liquid is 1600 over, and then I have 1600 minus, once again, 680. Okay, so now we just plug the numbers in and see what we get. So 1500 minus 680 times 2.5 plus 1600. Okay, so the top is just 1400 and the bottom is 920. So I have this divided by 920, so I get about 1. Yes, good job, Yadav, your calculations are very quick. 1.52 meters. Yeah, that's it. So we found finally that the H is 1.52 meters. And yeah, that's the question basically. So relatively straightforward. Once again, we applied the same principle, so nothing terribly challenging. Okay, I'm going to have a look for other things. Let's see, what else can we do here? Just reading a couple of questions now. Some of them are quite repetitive and similar to what we've done. Fuel gauge for gasoline tank in the car is reads proportional to the bottom gauge pressure. Okay. Okay, so the fuel gauge of a gasoline tank in a car is proportional to the bottom gauge. The temp most given in the question. Yeah, so the temperature in the question is, I think most of the time it's going to be 20 degrees Celsius. We don't really care about the effect of temperature on the density. Yeah, we're gonna, usually you look at temperature if you consider anything related to thermodynamics or heat transfer, but in this case we don't. Most of the questions are considering fluids at 20 degrees Celsius, and yeah, it's just that you don't take into account any kind of variation of the you don't take into account any variation of the properties of the liquid with respect to T. Um, yeah, I mean, if you're not here, you can't really attend the lectures because we don't broadcast them online, although there might be some recordings. But yeah, I think Aula has sufficient information so you can follow along and then be prepared when you come here. So yeah, that's all good. Okay, this is interesting. I haven't even come across this type of question before, but we'll see. So this is a text and there's a diagram as usual, which is this. Okay. So this is related to what happens when you accidentally put in when you accidentally get water in your fuel tank in the car. So this question refers to that. It doesn't refer to the consequences, but it's related to that idea in a sense. So we know that the fuel gauge of a gasoline tank in a car reads proportional to the bottom gauge pressure, as in figure 222, so the figure below, if the tank is 30 centimeters deep. So we know that the total depth of the entire tank is 30 centimeters, like this. So from top to bottom, okay? And accidentally contains 2 centimeters of water plus gasoline, so it should just contain gasoline. How many centimeters of air remain at the top when the gauge erroneously reads full? Okay. So the gauge pressure in the fuel tank is meant to just think that you just have gasoline, and if you have any other fluid there, it has no way of knowing that, because the gauge pressure, all it knows to do is to read the pressure. So in this case, in this question it will read full, even though it's not full. And the reason for that is because a truly full fuel tank, so if I draw this thing here again, so this is where the pressure gauge is and so on, and then what happens is if you just have gasoline in here, right, then this should all be full. So the reading full in an ideal case should refer to you having gasoline all the way through this tank. So this is the ideal case. When you go to the gas station and when you fill the tank with gasoline, this is what you expect to have. But in this case, in our problem, we have some extra water that infiltrated somehow, and that water is more dense than gasoline. So how do we know that? Well, first of all, the question tells us that's the case. Yeah, so we know the density of the gasoline divided by the density of water is 0.68. Yeah, so we're pretty much being told that the density of gasoline is 680 kg per meters cubed. So other than gasoline, we have 2 centimeters of water height, basically. And this water is more dense than gasoline, so it creates enough pressure to make the gauge think that the whole tank is full, but in reality it's not. In reality we have gasoline, but we also have water and we also have air. So the combination of water and air is such that the pressure gauge thinks that we have a full tank of gasoline, and this is what the driver will see on the board shown. So let's have a look at how to actually do this. So it's not a difficult problem. It's kind of like getting your head around what it wants, and then we start writing things as usual. So the only thing to do here is to just write the hydrostatic pressure. I think that's literally it. So the gauge pressure is due to all those layers pushing down. And again, I'm ignoring atmospheric pressure. So on one hand, we have air, which we don't know what the height of air is. This is the unknown. So we have air pushing down. So we've got density of air times G times H. Okay, and then plus we have gasoline. So we have density of gasoline times G times well, we don't know how much that is either. So this is going to be based on H. So we know the total height is 30 centimeters. We know we have 2 centimeters of water. We have H centimeters of air. So the remaining bit should be, so 30 minus 2 is 28. So this should be 28 minus H centimeters of gasoline. But I'm not going to use centimeters, I'm going to convert it to meters, so this will be 0.28 minus H. Okay, plus the water, so plus density of water, G, and then this is times 2 centimeters, so 0.02. Okay. Right, so now what we have to keep in mind is that the pressure gauge thinks that the whole tank has gasoline in it. And if we had gasoline all the way through the tank, the pressure, which caused the gauge to say full, would be just density of the gasoline times G and then times 0.3. So if you just have gasoline, the pressure here is this, basically. So this is the pressure that is being read, but we don't have purely gasoline, we have 3 different fluids, and therefore this pressure has to be equal to this pressure, because this is the pressure when we have gasoline and the tank is full. This is the pressure that we have when we have all those 3 liquids, but we still get the same pressure according to the gauge. So we just equate the 2 sides. So we have density of the gasoline times G times 0.3 equals, and then all those things. So density of air, GH plus density of gasoline G and then 0.28 minus H plus rho WG, and then we have 0.02. Okay, I can cancel out the G, and then we have to rearrange to get H out. So to do that, let's see how can we get this in an easy way. I think in this case, moving the H terms on the other side makes more sense. So I have H, and then I have density of gasoline minus density air, and that is equal to density of gasoline times 0.28 plus density of water times 0.02 minus density of gasoline times 0.3. Okay, so we have H equals, if I factorize, if I put those together, you go 0.95 approximately 1. Okay, I'll keep that in mind. So density of gasoline times 0.25 plus density of water times 0.02 divided by density of gasoline minus density of air. So this is, let's see, we know this is 680 times 0.25 plus 1000 times 0.02 over density of the gasoline, that's 680 minus 1. I think we can say that's 1.2. So this is 680 times 0.25 plus 1000 times. So I'm getting something quite different. I'm getting roughly 28 meters. Which is strange. 0.28 for the air. So what's happening here? So let's double check the expression for the gauge pressure. So I have density of air times G times H, so that's fine, plus density of the gasoline times, well, I'm checking my work again as well, because that H doesn't really seem right. Yeah, so anyway, let's see. So we've got density of the gasoline being 680, and this is 0.28 minus H plus density of water times 2 centimeters. So 2 centimeters clearly 0.02. Now if we just have gasoline, pressure is this. Right, and then when we put things together, we have density of gasoline times 0.3. This is fine, this looks fine. Plus density of water times 0.02. Okay, let's see if something happened when I rearranged. So we have H times the gasoline minus the water is 0.28 times the gasoline. Oh, okay, I see the issue. I've done a silly mistake when I was subtracting things. So yeah, 0.28 minus 0.3, that's not 0.25. I did 0.28 minus 0.03, but this should be, so this should not be right. So 0.28 minus 0.3, this is minus 0.02. And everything else should be fine. So let's get rid of this. And this becomes 0.02 density of water minus density of G, and this is rho G minus rho air. Okay, so we have 1000 minus 680 divided by 680 minus 1.2. Okay, well, let's see. So we have 1000 minus 680 times 0.02 divided by, we have 680 minus 1.2. Okay, so the answer is 0.00094 meters, which is 0.94 centimeters. So yes, Yadav, well done. You actually got it the first time around. So yeah, again, this is what you should do when you have, when you don't have the answers with you. Always do this kind of sanity check. So I think my previous answer was 0.28 meters, which was clearly wrong. So something has to, something had to have, something went wrong somewhere basically. And yeah, in this case it was just a silly mistake. So yeah, they can creep up on you. So that's it. We have therefore an amount of air which corresponds to a height of 0.94 centimeters, like this. So approximately 0.25 meters. I'm not sure what you mean by that. What does 0.25 meters refer to? Yeah, but in any case, that's the problem basically. So quite interesting. It's an application that I haven't really seen before in terms of looking at the actual fuel tank, which was filled with some impurities such as water and air. But here we go. Okay, let's have a look at maybe one more thing. Okay, so I have something here which is oh yes, yeah, that's what I wrote first. Yeah, obviously it was not correct. Yeah, so that's this 0.94 centimeters. That's the correct answer. Okay, now I'm looking here at something which is it's a bit more hardcore than what we've been doing so far, because it involves 5 different fluids actually, because we have air as well. And I'm not even sure if I know the densities of all of them. So I know mercury, water, air. I would have to look up the others. Okay, so let's start from where this question was. So this was 222. So 222, so that's sorted. Tell me the absolute pressure at point A. Okay, this one is pretty simple, and we've done it before. Okay, fine. I think what I'll do is I'm gonna wrap up the stream with one final problem, which is this one. So let's copy paste it here. So that's the final thing I want to cover. So we know that in this diagram with all those well, it's only like one tube and 2 vessels, or 2 pipes actually, because I believe points A and B are considered, or can be considered, to be within 2 pipes which are running into the screen or out of the screen basically, and you're just measuring the pressure in the 2 pipes based on all those unnecessarily complicated liquid systems, because you have mercury, you have benzene, you have kerosene, well, fluids, they're not all liquids, but we have water, and yeah, so we've got 2 pipes. One of them is carrying benzene. I have no idea what the density of this is. We have this pipe which carries air, which we know the density of air at 20 degrees is roughly 1.2. I'll have to look up the unknown ones on Google. Then we have density of water as 1,000, like this, and what else? Mercury, so I know mercury as well, so Hg stands for mercury in the periodic table, so I'm gonna write this as 13,000, okay, almost 600, I'll just call it 13,600 because it's simpler this way, kilograms per meter cubed. And then I have the other two liquids or fluids rather, so let me try to look them up in the book first. I have kerosene, which why is it so hard to find? I can find a lot of problems with kerosene, but none of them tells me what the density is. This is, oh, okay. I go to the appendix. So, what's this? Temperature. No, I don't want viscosity. I want... Yes, okay. I have it. So, there's actually another table, which... I should have used that one instead. So, that's what I'm given. Okay, let me go back to the question in the meantime, and then we can continue. So this is question 231. Okay, cool. Benzene is 876. Oh, thanks for looking it up, Yadav. That's very nice of you. So let's see, are those the same as what I have? So kerosene is 804, according to what I have. Yeah, so pretty close. And benzene is 881. Yeah, so yeah, you got very, very close values. It's arguable that, you know, whether mine are correct or yours are correct. So I'll just use the ones from the book as, yeah, it doesn't really matter which ones you use, to be fair. The numbers will be different in the end, but whichever ones are fine. The method is more important anyway. So the benzene is 881 and the kerosene is 800, and so I have it as 804. So they're pretty close. Yeah, they're quite close together, and then we have the other three which are wildly different, so we have them as orders of magnitude different from each other, air, water, and mercury. Okay, so what do we have to determine the pressure difference between points A and B? So all this system of pipes is meant to give us the pressure is meant to help us find the pressure difference, because I believe in this question you can't actually figure out the pressure of A or the pressure of B by itself. I think you have to, you can only figure out the pressure difference, and we'll see that this is actually the case. So other than that, there isn't really anything else other than just a bunch of drawing horizontal lines all over the place. But we have to be, you know, smart in terms of where do we draw those lines. So let's see. So I would start on the left, and I would draw my first line maybe here like this. Okay, so let's label some points. So I'm gonna call this point here, wait, do I want to use that one or do I want to use the one above? Let's think about this. So Do I want to use that, or do I want to go? I don't think it actually makes a difference, but it might be convenient in the long run. So, okay, I'm gonna draw my first horizontal line here. And I'm gonna call, this is not, it's slanted. It has to be perfectly horizontal. Okay, good. So I have point 1 here and point 2 here. And I'm gonna say that the pressure at 1 has to be equal to the pressure at 2, clearly, because I have two liquids or two fluids which I have the same fluid on both sides and they're connected through the tube and they're on the same horizontal, so the pressures have to be equal. Okay, so the pressure at 1 is equal to the pressure at A, so the pressure in the pipe, plus then we also have the pressure due to that column of benzene, like this, right? So that's going to be density of the benzene times G, and then times that small column which should be 12 centimeters. So that's going to be 0.12 in meters, okay? And the pressure at 2, so the thing with the pressure at 2 is that we need to add something here. So clearly the pressure at 2 is based on the thing that's sitting above, but we don't know what the pressure here is. What color can I use? This one. So I don't know what the pressure here is, although that pressure is pushing down on point 2. We don't know what it is, and what I'll do instead is I'm gonna label it in a way. So I'm gonna call this P, I'm gonna call it P star. So this pressure here is gonna be P star, and I'm gonna say that the pressure at 2 is equal to P star, right? Because it's clearly pushing down on 2, but not just P star, we also have this this other column here, which is, do we know how much that is? That's the question. So we know the water on the right is 40 centimeters, but I don't know how much that height is. But what I can do is I can label that as well. So what I'll say is that, okay, I'm gonna say that this height, I'm gonna call this capital H. So we've introduced two more unknowns, but what I'm relying on is that the unknowns will cancel out, and I think they will have to cancel out, because P star and H will appear in the equation for this horizontal line as well. So there will be some cancellations which will make my life easier, but until then we'll assume that, you know, they will have their specific variable names. So we've got P2 is equal to P star plus, now we have this column which is pushing on point 2. So that fluid is kerosene. So we have density of the kerosene times G, and then the height is going to be H minus 8 centimeters. So H minus 0.08, like this. And I think that should work in this case. Yeah. So we've got the height, the unknown height, which is H, and we have the P star, and we know, well, we don't know this height, but I called it H, so I'm just doing a quick recap. And then what's pressing down on point 2 is H minus 8 centimeters. Okay, so far so good. Okay, let me use this diagram again. And this time I will do another horizontal line. Yeah, I'll do another horizontal line test. So we've done the horizontal line test for points 1 and 2. So that's, for now, that's sorted. I can't really proceed any further. What I'll do now is I will do the same thing, but I will do it at the boundary of water and kerosene. So I'm gonna do it here. Let's use a thinner line, like that. So let's remember what I was saying previously. So I was saying two things. First of all, the pressure here, I call that P star, and I also said that I want this height to be equal to have the variable h, basically. So what I can say in that case is that this pressure, which I'm going to call 3, is going to be equal to this pressure, which I'm going to call 4, because we're crossing through the same fluid twice. So we've got P3, which is equal to, so P3 is equal to P star plus, so on top of 3 we have P star pushing down on it, plus this much of kerosene. So that amount is actually equal to H minus 40 centimeters, if you think about it. So that's going to be density of the kerosene times G times H minus 40 centimeters, or 0.4. Yeah. So just checking if I converted everything to SI units. Right, so that's basically it for P3. So we have P star, and then we have that tiny amount of kerosene that's sitting on top, which is density of kerosene times G times H minus 40 centimeters comes from here, by the way. Okay, and then P4. P4 is actually, I'm not sure if this is going to give us anything new per se, but we'll try. So this is going to be equal to P star plus, once again, the density of the kerosene. So that's density of kerosene times H minus 0.4. So yeah, this is just the same thing twice. We're not really having anything new here. So I'm just going to ignore this. And if we do this again, so let's do another horizontal line test. This time I'm gonna do it over here like this. Okay, so let's see how what names we give those pressures. So I have, on this side I have 5, and this is going to be 6. So pressure P5 equals right. So let me add my my variable. So I have a P star over here, and then I have H all the way up from that line to the top. So that's H, and P5, the pressure at 5, is equal to the P star plus, and then we have the things which are pushing down on 0.5. So now there are two things, right? There is this bit, which is the kerosene. So that's kerosene G times H minus 0.4. Actually, you know what? I'm gonna move this a bit like this. So P5 is equal to P star plus, we have the density of the kerosene times G times H minus 0.4. So that's the P4 or the P3 from above. But then we have this extra column of water, right? And on 0.5, how much water do we have? Well, let's write let's write raw water G, and then the height of the water column is this right here, which is 40 centimeters minus 14. So that would be 26 centimeters, so 0.26 meters. And then P6 is going to be equal to the pressure at B. Yeah, because it's communicating with the air inside B. And then plus, we have this column of air, which is given by density of air times G, and then the height is 9 centimeters, so 0.09. Okay. Right. Yeah. So that's basically it in terms of everything we can write. So I don't think I missed anything. I'm just gonna double check though. So we looked at points 1 and 2, which were closer to the pipe A, and then we looked at the middle part, which doesn't really tell us anything new. And then we looked at that place near B where you have the interface between air and water. Right, so we have a couple of unknowns, but I think it's okay because things are gonna cancel out. So what I'll do is I'll rewrite, I'm gonna ignore those for now. So I'm gonna ignore, because those equations don't tell us anything particularly new. So what I'll do is I'll write this set of equations, and then I'll rewrite this set of equations. So for pressures P1 and P2, I have P1 is equal to PA plus rho B, so that's benzene G 0.12, and then we have P2, which is P star plus we have density of the kerosene times G times H minus 0.08. Okay, I'm just gonna double check those. I don't really want to make any silly mistake right now. So for point 1, we have PA plus density of the benzene times this height is definitely 12 centimeters, which is fine. And then this height is H minus, yeah, okay, cool, that's fine. So there's this, and then we also have those pressures. So we have P5 is equal to P star, I think, yeah, plus density of the kerosene times G times H minus 0.4 plus density of water G, and I think I actually used all the numbers in the question in the end. So P6 is equal to PB plus the density of air times G, and then times 0.09. So we ended up with this system of equations based on the physics. So once you go past the physics, you just end up with some equations that, you know, are not terribly complicated to solve. And we don't even have to solve them, we just have to find, remember, PA minus PB, or the other way around. Determine the pressure difference, yeah. So we have to find PA minus PB. And I'm just going to double check P5 and P6 again. So P5 is P star plus kerosene. Yes, and then I have H So this amount of kerosene is H minus 0.4. Okay, that's good. And then I have the water, which is this much. So the water is 40 minus 14, which I'm pretty sure is 26. And then for P6 we have PB plus the 9 centimeters of air for hydrostatic pressure. Okay, that looks fine. So remember, we were doing the horizontal line test, right? So P1 is equal to P2 and P5 is equal to P6. So if I make them equal to each other, I should get something interesting in the end. So I have the two equations being equal to one another. So I have PA plus rho benzene G 0.12 equals to P star plus this. And then I also have those two, so I'm gonna start with P6 first. So I have the PA and the PB one under each other, and that's kind of like a trick to be able to subtract them easily. Plus rho air G 0.09 equals P star plus density rho K G H minus 0.4 plus density of water G 0.26, and that's it. So now the only thing left to do is to subtract the equations, and the nice thing about it is that my unknown pressure P star and my unknown height H will cancel out if you subtract the equations. Now I'm only figuring out, do I want to subtract, do I want to PA minus PB or PB minus PA for convenience purposes? So I think I might want to do PB minus PA. Actually no, it's fine, I'll do PA minus PB, whatever. So either way works. Okay, so if I subtract the two, I have PA minus PB, and then I have plus rho B G 0.12 minus rho air, so I'm subtracting them kind of like one by one, equals. So the nice thing about it is that the P stars are gonna go, so those cancel, this cancels with this as well, and then I have rho K G, that should have a minus in front. So I have minus rho K G 0.08 plus, and then I have rho K G 0.4 minus rho water G 0.26. Okay, so I did this side, this equation minus this equation, so I did this minus this, like that. And I know everything at this point, so except PA minus PB. So if I keep PA minus PB here, let's see what we get. Yeah, I have all the fluid densities and all the heights go on the other side. So we have density of the benzene G 0.12 and then plus density of air G, and then we have 0.09 minus density of the kerosene G 0.08 plus density of the kerosene G 0.4 minus density of water G 0.26. Okay, so now we can plug the numbers in, or the rest of the numbers. So unfortunately we have a G that we're gonna carry with us, but I'll put it at the end. So for benzene I'm using 881 times 0.12 plus, then I have the density of air, which is 1.2 times 0.09 minus density of the kerosene, that is 804 times 0.08, okay, plus density of the kerosene. So I have another density of the kerosene here. Is that right? Yeah, that should be right. Okay, so I'm just not using mercury. Yeah, so I have density of the kerosene again is 804, I think, times 0.4 minus 1000 times 0.26, and the whole thing is multiplied by G, which is 9.81. Okay, so if we put numbers in, let's see, so minus 881 times 0.12 plus 1.2 times 0.09 minus 804 times 0.08 plus 804 times 0.4 minus 0.26 times 1000 times 9.81. So I'm getting a value of minus 1062.74 pascals roughly. Okay, so yeah, this seems to be the pressure difference between points A and B. Yeah, so I have about so we have about 1062.74 pascals between the two pipes, pretty much. So we've used centimeters, we've used the right units for we've used meters for the heights, we've used densities for all the liquids, using the right values as much as we could have, and yeah, I think that's that should be fine. So minus 1062.74 pascals. Okay. All right. Would you post more similar questions? To be fair, I don't think I have to, because this book is on the Aula page. So I posted it under resources, and you can find this exact book, and you can go through the questions yourself if you want, or even more questions. And they have answers at the end as well. So just keep that in mind. Okay, so hopefully this was insightful in terms of looking at some hydrostatics, some new hydrostatics questions, and maybe I'll do this again in the future. So during the next couple of topics, I might do one more stream or two more streams. We'll see how it goes. But yeah, thanks for joining. Thanks for watching, and I'll see you next time. Have a good evening, a good day, whatever your time zone is. Enjoy, and I'll see you next time.